Hello, my name is Christopher Figuera, and I am doing my presentation on RSA encryption for Project Codebreakers. So first off, RSA encryption is a type of public key cryptography. Uh, First off, I wanted to walk you guys through what public key cryptography is. It's a little bit confusing at first. So it has two names. Public key cryptography is otherwise known as asymmetric cryptography, and it's a system of equation where you use two keys of encryption. Um, these keys will be similar in some type of mathematical relativity, and they're used in tandem as a pair. Um, you first have what is described as a private key, and you have what is described as a public key. So, a private key is kept by the creator of this mathematical relativity key, and it's used to decipher and encode plain text. So let's say that I wanted to encode the text D, and then it would be transferred using my private key to some other letter F. So it'd be harder for somebody looking in to, or like looking through my emails or something to say, oh, this guy sent D, but in reality I sent F, and they'll be like, oh, this guy sent F. Now, I can give somebody a public key, and basically what this public key does is that I can use it to also decipher and encode plain text. So let's just say I have a friend named Tim, and I give him my public key, and I send him the letter A, and then it gets encrypted into D, so he gets sent D. And then using his public key that I gave him, it gets decrypted into back into A. And this can work vice versa, where my friend can send me his public key and he can send me something in plain text that's been encoded by his private key, and then I can decipher it using his public key that he gave me. So it's basically like giving somebody your phone number and then sending them a text, but with an extra step in the middle. It's basically just used to make sure that your data is safe in transit to make sure no one's snooping in on it. So going into RSA and how it's different, RSA came along when it was created by three different guys, Ron Rivest, Adi Shamir, and Leonard Edelman in 1977. All the YouTube videos that I've watched on RSA have described these guys as basically living legends and geniuses in our time. So there's that. Little fun fact that I discovered while reading and researching was that an equivalent system was created 4 years previous in 1973 by an English mathematician named Clifford Cox, who was working for the British Intelligence Agency at the time, at the GCHQ, which is a government communications headquarters. It was never deployed. Basically, his superiors thought that the process was too expensive, just due to the massive computer power that they needed in terms of RAM and processing speed, all of that. It was just too much money for the program. Um, the way I describe RSA, and it's been described to me, is used more as a niche version of the public key cryptography system, and it's used in tandem with another encryption system, the AES. Basically, it involves number theory, a lot of number theory in this one. You need the use of two prime numbers, P and Q. You find the product of those two prime numbers, P and Q. You get N. You have a phi function and co-primes of that number N, and then you have your numbers E and D, which are going to be specific to a public and private key that you give out. And those also have two different types of conditions that we'll get into later. So here's a basic, very, very, very basic flowchart of how this will go. You see the left side here with the sender and the plain text, kind of like how I was describing with me and my friend Tim sending stuff together. So normally, if you disregard the bottom, you would just send your plain text, and then it would get to your friend as plain text. But if you want to keep it safe and encrypted, you're going to go ahead and use RSA. So here we have the sender, that would be me, using having sending a plain text and AC2 code, which is basically like A, B, C, D, the alphabet and the numbers, yada, yada, yada. You have an encryption key, and it follows the formula where we saw earlier, where it's E and M. E will be your encryption, or the E that we saw earlier. It's a part of your private key. And then you're sending it, or using M, which is going to be your modulus, which will be for later. You encrypt it in cipher, whatever you want to call it. It basically gets transformed to something completely different, which we call the ciphertext. Ciphertext is basically saying, or is basically my example of saying that I sent my friend A, and then the ciphertext encrypted it to D, and then my friend gets D, and then he decrypts it using the decipher or the key, um, and he gets A. This can be reversed. So I was using the example of that I have my private key and I send it to him, and then it gets enciphered, and then he deciphers using his public key. But in reality, it could be reversed, where he is sending me a message using his public key that he got from me, and then I'm deciphering it with my private key. So it works both ways. It's pretty nice. Now, in the examples ahead that I'm going to use, we're going to be using pretty small numbers, but I just wanted to show you guys how large the private and public keys can get. And it can hold up to about 256 bytes, which is pretty big. It's about, like, I want to say over 1,000 bits when 8 bits is in a byte. So you can convert this private key into hexadecimal and then yada yada yada. These are huge. So we're going to be using a bit of a smaller one. So I'm going to go through the steps first. So step one, like I said, you're going to have a number P and Q. So start by defining your integers P and Q as prime numbers. From this example, I'm going to use P is equal to 2 and Q is equal to 7. Then you're going to find the value of n. N is pretty simple. You're going to multiply your P and Q values together in order to get your n value. So the example here is that we have the formula P times Q is equal to n, and your P is 2, and the Q is 7 from earlier, so your n value is going to be 14. Step 3, the phi function. We did this earlier in the year in exam 3. Um, Basically, to get your phi function value of n, you list out all your numbers starting from 1 to your value of n. And then you remove all the numbers that share a common factor with n excluding 1. So for 14, I made a little chart here. Left side is listing all the numbers from 1 to n. Right side is removing all multiples of 2 and 7, since that was our p and q values, which we used to multiply up to get to 7, or to 14, since that was our product. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 are our numbers listed out. And on the right side, we remove all the multiples of 2 and 7. So the yellow is what's highlighted and which are the coprime and which are our answers. So we get 1, 3, 5, 9, and 11, and what's eliminated is 2, 4, 6, 7, 8, and 12, 10, 12. Here, so you can see again, we have 1, 3, 5, 9, 11, and 13 as our numbers. So now we choose our E. In order to choose E value, there are two rules that have to be followed. One is that it must be followed that 1 is less than E, but it's also E is also less than the phi function of n. So here we had 6 numbers, so our phi function would be 6. But it also must be coprime with n and our phi function of n. So here's our coprimes of n. Actually, I'll go ahead and skip to step 4. So we're going to go ahead, or we're going to skip ahead to the examples. So the first condition, where E can equal either 1, has to be greater than 1, but less than 6. So here, E can be 2, 3, 4, and 5. But we have to follow our second condition, where it has to be coprime with 14 and the phi function of 14, which is 6. So here I have highlighted 3, 5, 9, 11 again, since that's the coprime of 14, but we also have the coprimes of phi 14, which is 5. So E can be 5. Then you choose your D value. It's going to be for your private key rather than the E value for your public key. So for your D value, you must follow the restriction that D times E mod phi function of n is equal to 1. looks a little bit confusing and daunting at first, but we're going to go ahead and simplify it in the next slide. Here again, I have the equation and I have our values listed that we already know. So e that we got from earlier is 5, and then our phi function is 5n is 6. So we need to find a number in where d times 5 mod 6 is equal to 1. So I made a little table here where the orange row is going to be a value that we plug in for d, we're testing right now, and our black row is a remainder. So for 1, we get 5, 2, 4, 3, 3, 4, 2, and then we see 5, we get 1. That's really nice. But you can keep going. It's kind of like the system of congruencies that we had earlier in the year, where you can say, oh, since 5 is a number, we can also use 11. 11, you get a remainder of 1, boom. So I chose 11 for the next step, and here's a review. So you start with two prime numbers, p and q, multiply both numbers to get n, find the phi function of n, choose a number e with restrictions of 1 is greater than or is less than e, but is alt li is less than phi function of n, must be coprime with n in that phi function, and then choose a number d with restrictions that d times e mod phi function of n is equal to 1. So we're going to go ahead and get started with actual practice since I'm running out of time. This goes with the examples that I've been using earlier. So the encryption key that we have, which is public, is 514, which follows E capital N. The plaintext received is the letter E. Knowing E is the fifth letter of the alphabet, we assign E the value of 5. Using the formula 5E mod N, we get 5 to the power 5 mod 14. See how everything plugs in. You can actually at the base of the exponent, you can actually exchange 5 with C, and then C would be our ciphertext. Or sorry, M would be our main text, C would be later on. So we do the power. 3125 mod 14 is equal to 3. The third letter in the alphabet is C. C is also our ciphertext. So we're sending an encoded text of C in the place of E. Now with the public or the private decryption key, 1114 follows DN. Remember the D from earlier and the N from earlier. We're going to go ahead and apply them in here. So 3 to the power of D mod N is going to be 3 to the 11th power mod 14, which is equal to 177,147 mod 14, which we get 5. Deciphering 5, we know that the fifth letter of alphabet is E, the plain text which is first sent. Moving to the next example, I'm going to do a little bit of a word problem here. Chris wants to send an encrypted message M, and he wants to send an encrypted message to his friend Tim. Tim's public key is 333, and his private key is 733. What is the ciphertext that is sent when Chris uses his key? So, since Chris is sending the key to Tim, we want to use his public key rather than his private key, since we're only encoding and we want to see what is ciphered. So, Tim's public key is 333, which follows the order again of E, N, little side note here, you might see it written as a larger number first and a smaller number second. If that's the case, then N is going to be your first one and E is going to be your second one. Using M is equal to 13, since 13th is 13, M is equal to the 13th letter of the alphabet, we can use 13 to the power 3 mod 33, which is equal to 19. So the ciphertext being sent is 19. So the 19th letter in the alphabet is S. So he would see S, and if Tim uses his private key back on that of 7 and 33, he will get back M. Thank you guys for watching. I know this is a lot of information. It seems really hard, but I'll go ahead and drop some other links down in the discussion post. If you guys want to look up a little more at this, I know it's a little bit rushed because of time, but I hope you guys enjoyed watching it. And if you got any questions, go ahead and send some down.